Hello there, and welcome to this collection of notebooks and tutorials on multirate signal processing. This is a course offered by Professor Schuller at the Ilmenau University of Technology. I am Renato, and on this tutorial we'll continue talking about the DCT, and then we will move on to an introduction to polyphase representation. So let's get started. Another widely used block transform is discrete cosine transform. When you look in literature, you will find many different definitions of the DCT type 4, but this is the one we're going to use for this lecture. And you can see also in lesson number 2, we talk about the DCT. So the DCT type 4 that we are going to use has this equation here. We notice we have this squared root of 2 divided by capital N. We have this 0.5 here, this 0.5 here, and this analysis go from k going from 0 to n minus 1, and we have the sum from n going to 0 to n minus 1. So the characteristic here is the shift of 0.5 in the subband index k and at the time index n. So we have the 0.5 shift for subband index and for the time index. If we compare it to the DCT type 2, and we see that the DCT type 2 is defined by this equation here, we only notice the difference is this ck here, this coefficient, where the c of 0 is the square root of 0.5 and the ck is equal to 1 for k greater than 0, for k going from 0 to n minus 1. So observe that the only difference is that the DCT4 also has a shift of 0.5 for the frequency index k. The DCT2 is mostly used for images and video coding, whereas the DCT4 is mostly used for audio signals. So using the definition of the DCT4, we can now construct the transform matrix and extract the equivalent impulse responses. So the analysis transform matrix becomes this here. And the impulse response of the equivalent analysis filters, they are the time reversed columns. So this is the impulse response of the equivalent analysis filters. So in this way, we get capital N impulse responses. So the synthesis impulse responses are simply the rows of this transform matrix, which in this case is identical to the columns. So we have here the synthesis impulse response. So here we have our transform matrix, and then we get the impulse response of the analysis filters as the time reversed columns of this matrix, and the synthesis impulse response are the rows of this transform matrix, and in this case is identical to the columns. So we see that they are simply the time reversed analysis filter. Since here we don't have time reversal. Here we have perfect reconstruction filter banks with critical sampling, both desirable properties for coding. But our equivalent filters, they are restricted to a length of capital N. This leads to filters which do not really have good frequency responses. We can get wide transition bands for our bandpass filters relative to the width of the passband and not enough stop band attenuation. So in Python, we can get the transform matrix for the DCT using this here. So here we're starting with empty zeros, 4 by 4 matrix, n is equal to 4. Then we will iterate through n and k, and we will set these values here, and then we have our transform matrix for the DCT4. And now we can plot the frequency response of the analysis filter, for instance for subband k equals to 0. So now I'm importing SciPy signal, and I'm importing matplotlib pyplot. So we will plot the SciPy signal. Once again, we use fracz to get the frequency response. It's done here. This time we're using subband k equals to 0, and then we plot here, and we see the magnitude response for the DCT4 subband k equals to 0. Here we have our normalized frequency going from 0 to pi, and here we have our magnitude in dB. So observe the low stop band attenuation of less than 20 dB. A solution is to allow filters with longer impulse response, longer than the block size n. This would lead to non-square transform matrices, but non-square transform matrices are not invertible in general. We can only obtain a pseudo-inverse. Hence, we would lose perfect reconstruction, which is a problem. Alternatively, we could have overlapping blocks, which could provide perfect reconstruction, but then we would lose critical sampling. Again, a problem for coding applications. Our goal is to obtain longer filters, have the same block length for critical sampling, and perfect reconstruction. This means the transform matrix approach, or views, comes to its limits. We need new tools. This leads us to the polyphase representation, which can be seen as an extension of the transform matrix approach, or as a mixture between the transform view and the filter bank view. We start our journey into polyphase representation taking a look at the analysis filter bank. So we start with writing our analysis filter with FIR filters of length capital L and downsampling operation in terms of our block index M and an in-block or phase index N with N between 0 and capital N minus 1. The original formulation for our subband signals for the convolution and downsampling with phase N0 was given by this equation here. Here we have our phase N0. Here is downsampling, and we have the sum N going from 0 to L minus 1, where L is the filter length of our FIR filter. In general, we assume that the filter length L is an integer multiple of N, and we can always zero pad it if necessary. We can now split this sum into an in-block processing with the phase index N that runs from 0 to N minus 1, and an out-of-block processing with the block index M prime, which runs from 0 to the end, by using an index substitution. In this way, the index M prime corresponds to our downsampled index. To obtain the same ordering for the signal X as we use for our block transform approach, with its index N going up, we substitute N by M prime times capital N plus N minus 1 minus N, and we choose the downsampling phase as N0 equals to N minus 1, and then we'll substitute from here, and we'll go to here. And then we have here a double sum, and we have this M prime now replaced N by this here. And we'll observe that this is still our filter bank formulation, but the interesting part here is that the inner sum again looks like our block transform formulation with blocks or vectors of size n and an impulse response along the column vector of length capital N. We can reformulate or simplify the inner sum as a vector multiplication when we rewrite the impulse response Hn as a vector which contains a sequence of blocks. So this is now the impulse response h of n as a vector. And we will use the vector of input blocks given here. Hence, we will get this equation now here, which is exactly the inner sum of 8. So here was equation 8, and now we have here. Hence, using these two vectors, we can replace the inner sum by this vector multiplication and rewrite or simplify equation 8 to this here. So now we have the inner part of the sum is now like our block transform. If we view our impulse response h of k as one column reversed of a transform matrix. So again, this is the transform view inside the filter bank view with longer filters, which is why we also have the outer sum, the out of block processing. That's a convolution. The remaining outer sum now looks like a convolution again, but now with a sequence of blocks instead of samples. And we have a vector convolution, even here. Observe that our downsampling factor is now embedded in our block size. This has the advantage that we can now apply the z-transform to this equation to turn the convolution into a multiplication. First, we need to z-transform our vectors. So we start with the signal vector x of m in the time domain, and we can compute the z-transform of each element of the vector as polyphase elements, even here. So the z-transform of our signal vector x of m then becomes the polyphase vector. So we have here. Since we have n phases, we call this approach polyphase. We will use the same method for the vector of impulse responses. So we have here a vector of impulse responses, and then we will have the polyphase elements given by here. So this is our vector of impulse response, and then we have the polyphase elements, each one given by here. And the output of our case filter is still just a polynomial, not a vector or matrix. Even here. The result of filtering and downsampling for the case filter in the Z domain is then the following simple multiplication of vectors. Observe here we rewrote the analysis filtering and subsequent downsampling by this multiplication of vectors in the Z domain. For an implementation, we can convert this equation back in the time domain, starting with rewriting the vector multiplication as a sum over the phase index n. So we will rewrite this vector multiplication as a sum over phase index n. The multiplications in the Z domain become a sum with simple convolutions in the time domain, which is here. This is the sum over the phases of the convolution of the blocks. With this equation, we can now implement the polyphase structure in the time domain. So here we have a visualization of the polyphase elements and the blocks. So given a signal x of n and a downsampling rate of n equals to 2, we get the following blocks and polyphase elements. So we have blocks and we have polyphase elements. Let's try to have a better understanding of all this theory using a Python example for polyphase. So we will assume our signal x is equal to this array of numbers 5, 6, 7, 8, 9, 10, and we use n equals to 3. So then we get the signal blocks if x of m with m in a range as we need to fit the signal. So x0 will be 5, 6, and 7, and x1 will be 8, 9, and 10. We can use Python SymPy, and we use three-dimensional arrays or tensors to represent the coefficients of the different exponents of z in the third dimension. So now we are going to use SymPy. I'm defining here c as a symbol, and then the polyphase matrix now is a row vector with two blocks. So I'm defining here first xp, so zeros. So this is the size as a three-dimensional array, and then we have this x with 0 here is with 0, and then we have 5, 6, and 7, and here is 1, and we have 8, 9, and 10, and then we'll add these two, but this one as a coefficient for z to the power of -1. So we end up with this array here, and we have 5 plus 8 z to the power of -1, 6 plus 9 z to the power of -1, 7 plus 10 z to the power of -1. So the polyphase elements x n of z with phase 0 n from 0 to n minus 1 are given here. So the polyphase vector is, so we have this element here, this element here, this element here, and we have this polyphase vector. So we see that it corresponds to exactly the same as our Python output. Assume we have the first analysis impulse response given by h of 0 is 3, 4, 5, 6, 7, and 8, and for n equals to 3, then its polyphase vector is in general given here with our phases going down. And for this example, we'll take subband k equals to 0, and then we have this definition here. So in Python, again, we can calculate this. So the H polyphase matrix is a column vector with two blocks, and we are doing 5, 4, 3, 8, 7, 6, and then we're again we have this 0 and 1, and we multiply the 1 with z to the power of -1, and we will get this here, which is identical to what we have here. So filtering with downsample as a multiplication of the polyphase matrices x of z and h of z is done here. So what we're doing is we are doing a dot multiplication x of z and h of z, and what we have is this result here. So this is the filtering with downsampling as a multiplication of the polyphase matrices x of z and h of z. SymPy is a great tool for symbolic mathematical operations, but it's not really efficient for other applications. So we will obtain a faster implementation without SymPy if we go back into the time domain and write our polyphase matrices as polynomials with matrix coefficients. So this is what we are going to do here, where a, n, and bn contain all the coefficients of z to the power of -1, and capital NA and capital NB are the length of the polynomials. So we see here capital NA, capital NB, the length of the polynomials AN and BN. There's a mistake here. Let's just quickly fix. And then their product is given here. Remember that a0 plus a1 to z to the power of -1 times b0 plus b1 z to the power of -1 is given by a0 b0 plus a0 b1 a1 b0 times z to the power of -1 plus a1 b1 times z to the power of -2. Observe that in the z domain, this is a multiplication of matrix polynomials. In the time domain, this is a convolution of matrix sequences. So now what we can do is to write a Python function that will be called polmatmult. So it multiplies two polynomial matrices, so the arrays A and B, where each matrix entry is a polynomial itself. So those polynomial entries are in the third dimension. And the third dimension can be interpreted as containing the coefficient matrix of exponents of z to the power of -1. So this is what we're doing. We're defining here this function to do the multiplication of matrix polynomials, and we will use this later. Here we have an application example, and we will use this function we just defined for the multiplication of a matrix with polynomials. So let's take our signal and filter as in our SymPy example, but we will write them as polynomials of vectors x equal to 5, 6, 7, 8, 9, 10 with n equals 3, and its polyphase representation then is this 5, 6, 7 plus z to the power of -1, 8, 9, 10. Similar for our filter, we have this impulse response, and then the polyphase representation will be 5, 4, 3 plus z to the power of -1, 8, 7, 6. So these are polynomials whose coefficients are vectors. In Python, we simply store the sequence of vectors with the exponent as index in the third dimension. So this is what we are doing here. The exponents are on the third dimension for 0, for z to the power of -1, and then we are multiplying these two, and what we have is 70, 230, 187, and if we look back, is 7, 230, 187. And this is what we have here. Observe that this result in the time domain corresponds indeed to the one with SymPy in the z domain. Now we will define different functions that will make our life easier when we will work with polyphase. So here's a function to turn a signal into a polyphase vector. So it turns, for example, an audio signal into a polyphase vector that can be used as the input of our function that we defined, the polyphase matrix multiplication. So here is a phase that converts, given an input signal x, this is a row vector, into a polyphase row vector for blocks of length n. And this is what we are doing here. Another useful function is to turn a polyphase vector back into a sequential signal. So this is what we're doing, is polyphase to x. And this converts the polyphase input signal, it's p, this is a row vector, into a contiguous row vector for block length n. And we have here this function. So with these functions, the polyphase to x and x to polyphase, and also with our polymat mode, so the multiplication of matrix polynomials, we are now able to work with polyphase in a more efficient way and not using SymPy.